the size of the show now. I have added a little bit of commercial stuff, so I apologize in advance, but I can't go a little faster than those. All right, so what I want to talk about is a particular project, large project that I was involved in formal verification. This is joint work at the Technical University of Munich with two of my colleagues over there, Peter Lamik and Sudeep Kanap. And I'm going to talk about the CoCon project, what it is. I'm going to describe the context and its motivation, then its structure, and then show how we went and verified it. And finally, I'm going to describe some use cases. Because this is a real system running on a web server, so the intention is to have something that is verified and yet usable. But first, I wanted to start with who I am and what I want. I guess you all know me, so I'll go a little faster. Too much to say. I'm Romanian. I studied in the University of Bucharest. I did my bachelor's there. And then I did my PhD at the University of Urbana, Illinois, which is probably the best computer science department in the United States that nobody heard of.
I have no sex with UK.
It's famous.
Yeah, it's famous.
Right. It is. So it is a very good one, but it's like everybody heard of Berkeley, Stanford, MIT, CMU, and then Urbana is the fifth, actually.
Urbana is Champaign?
Yeah, it's the University of Illinois at Urbana-Champaign. Okay. And only at computer science and other things, so not overall. It cannot compare with Stanford's overall activity. In about my second year of PhD, I became very fond of a beautiful system called Isabelle. This is an interactive serial proving. I'll skip a little bit the commercial side, and a different text for this. I followed Isabelle at the Technical University of Munich, joining the Isabelle development team. And this year I came to Middlesex in Rochester.
So you're sort of steadily improving your university.
From now on, all the way down. You know that.
Obviously, yeah. Free falling.
There is clearly some local, at least some local opening there.
Well, yeah. I mean, I feel pretty stable inside. This is lots of point.
But I mean, joking aside, I think we have a very strong group, at least in the UK.
So if you fall something else, I'd be really worried.
Sorry?
If you fall something else, I'd be really worried.
Yeah. So I don't know if there are many places in the UK where you have such a sort of foundation dedicated.
I mean, there are a few, but I think we are.
Yeah, so there are a few. I mean, for instance, the Edinburgh.
Okay.
All right. So, how many people in the audience know what a theorem prover is? Everybody, except for Benedict. Do you know what a theorem prover is? So I mean, my point.
I also don't know.
Okay, so I mean, you're probably not very familiar with it. But the point was that almost nobody, assuming sort of this is a school setting, almost nobody heard of theorem provers, and everybody heard of programming languages. And the point that I wanted to make is that an interactive theorem prover is sort of a programming language of the future. So this is, in my opinion, and in other people's opinion, this is the right way to go in developing environments for programming. And I'm going to briefly justify this claim. So, what is really an interactive theorem prover? It is an integrated environment for performing mathematical constructions. So this is its original purpose, the original purpose of the concept. And then stating facts about them in a formal language, and finally proving the statement. So you can do all these things in a theorem prover. What's it got to do with the programming language? Well, a program is from an abstract point of view, a mathematical construction, an executable one, and you can write things as you would write in a functional programming language. Most of the theorem provers have a functional specification language where you can define data types, such as list of naturals in this example, and state and define programs. This one, in this example, let's say you define a sorting function, takes a list and returns a list, and you just program it as you would do it in ML function, in any functional programming language. Then you can define a specification, what you would like the program to do. For instance, you can define an is-sorted predicate. Here I define it in logical form, so I state for a list that it is sorted for a list of numbers, but it can require obviously an executable form. So far, nothing special. This is also something that is programmable. But what is special is that instead of going about testing that the function satisfies the specification, you can actually prove this once and for all. So you can state a theorem, and the fact that, for instance, after you apply the function, the list is sorted. This is a very, very simple example. And then you can prove the statement. I have started a template of a proof here. This is some proof assistants, including my favorite one, offer a very high-level specification, a very high-level proof language that is sort of mathematically pleasing. You can do the proof in a similar fashion you would do it on paper. It's just that you can, the things that you would say are obvious or follow immediately, you can just approach them with automatic tools. So basically, the theorem provers are getting better and better at automation, and this is very important if we want to use them at offering support for programming languages. So in my opinion, the only way to sell theorem proving or to bring it into mainstream, to make more people hear about it and consider it, is to apply this to programming language environments. And the main idea here would be that users of this environment would not need to engage in proofs unless they want to. So unless they want to be explicit about certain properties about their programs, but they would like to offer several things off stage in the background. And the difference between a theorem prover and a plain programming language is that the theorem prover knows what you do. Let me give you a particularly fancy example of this. Some people really prefer to test their programs. So some people actually, if you give them a mathematical proof that the program is correct, and a bunch of test cases, if you say unit testing, suit, they would still prefer the testing. So they would still trust the testing more. And there's a very nice line of work that actually deals with this. And essentially, this is based on something called relational parametricity. And essentially, the main idea is that if you verify that a program operates as expected on a finite number of cases that are chosen to be sufficiently varied, and the program is uniform enough, parametric technically, then you can infer that the theorem actually holds. So you can sort of give the illusion of testing, or basically just verify a few tests and actually come up with a proof that this testing is complete in a suitable sense. And this kind of support I have in mind. Okay?
So I have a question. So,
Yes,
so,
please. By the way, yeah, proceed around me.
so what is the formal definition of the theory in this context?
On theorem?
Yeah, in this context.
Well, it is.
So clearly, it's not a general mathematical theory.
It is. So you can.
Well, but not. I mean, there are. I mean, you can't have things that check proofs for theories. Yeah, you cannot check everything.
Right, yeah, you cannot automatically check everything. So the idea is that to have sort of a boundary that is not primarily fixed between things that can be checked automatically and things that can be obtained by interaction. So you have many theorem provers, or rather the logical side of theorem provers, establishes certain decidable fragments, where you know that if the theorem has a certain format, then you can prove it automatically. But this is not how automation, this is not how mainstream automation goes. Typically, you just try various methods. So you basically work in a highly undecidable environment and you apply certain heuristics for trying to finish the goal. So basically, you don't have a decidable logic, but try to obtain dynamically bits and pieces of decidability.
Okay.
For instance, this is how so-called ITPs, automatic theorem provers, work. It's first order logic, arbitrary first order logic, undecidable, but yet they go and prove things by smart search strategies. Of course, this is problem dependent.
So also series theorems have been proved, like the four-color theorem
Yeah.
and
Right.
the odd order theorem, series mathematical.
By heavy interaction.
Yeah, but that's what I mean, so yes, of course.
Yeah, sure, not completely.
Because
Mm.
there is an instability to theorem, so you
Yeah.
can't have something that.
Yeah, obviously. So so concerning application programming, typically programmers, they know why the program is correct, or they hope that the program is correct according to a criteria, and they are willing to put a little bit of effort into statements, but they don't want to start proof, lemma, and so on. So they don't want to see this kind of interaction. This is part of the reason why the Koch theory program, one of the major theory programs, is so successful, because it has this paradigm of process programs. So you don't do proofs, you just program your arguments. All right. So there are a few challenges. Some of them I think I already mentioned. Towards moving IDPs towards mainstream programming environments. First of all, there is a need for convenient abstractions for programming. This is sort of a goal that is shared with programming languages. Efficient execution. Theory provers were not designed with execution in mind, but in the future they could be as efficient as a mainstream programming language. Currently, most of the provers go for something sort of a compromise. This is an automatic means to extract code in a real programming language. So basically, write your program in a theorem prover, prove what you have about it, and then use a trusted component that is transforming your program into an isomorphic program written in a programming language. For instance, Isabelle targets 4 programming languages: OCaml, Standard ML, Haskell, and Scala. So this is a temporary solution for this, and it uses this trusted component. So we have to trust that the extracted program does the same as the specified program. Right, and I mentioned very discrete backstage support for the user, and this should be based on powerful automation. A little bit on the philosophical side, another challenge in programming languages, in theorem provers, is this question of reliability. So this is Latin, quis custodiet ipsos custodes. It means who's guarding the guardian. So a theorem prover is sort of aimed at certifying that certain things cannot go wrong, but who's going to certify it? And we know that self-verification is impossible. This is, I'm not going to insist on this, since the commercial side of this is not exploitable to this audience. But this doesn't stop people to engage in self-verification projects. I believe this trend started with John Harrison, and it has been taken over. And the idea is that you put Gödel aside, and you verify what can be verified. So you verify relevant parts of the logic in the logic itself. And there are some interesting results. Okay, but I'm not very interested in fighting with Gödel. Basically, these are my areas of research, and I'll be happy to discuss more about this in the future. Maybe give a talk on either of these topics. But for now, I will move to. Okay. There's a little bit of advertisement in that, so it's a commercial break. Theory provers are becoming more and more important. They are everywhere in the news. This is just a poor selection of what's happening. There are many recent results and acknowledgements. We have interactive theory proving listed as by the MIT technology reviews in the top 10 technological breakthrough approaches, and this is thanks to the verification work of an operating system done at NICTA by Jürgen Klein and his team. We have a very nice picture of Isabelle shown in this news entry. This is actually a lady researcher at NICTA, but they chose her as a front end for this presentation.
Her name is not Isabelle.
No. Her name is June Andronik. And we have the software, not software of the year, the system software system award for 2013 going to Koch. This is a sort of a fruitful competitor for my favorite prover, Isabelle. And this is a very, this award offered by the ACM actually goes to serious software in general. Theory provers have made it easier. In the last 10 years, we had this prover and the Boyer-Moore prover, also known as ACM2, received the award. And this is a very select company, as I said. So it's Donald Knuth Tech, it's GCC, and so on. So it's very serious software that received this award. Based on the analyzed impact. You also have recent verification successes, recent success stories about verification. Raja, I think, mentioned Kepler's conjecture or the four-color theorem. The four-color theorem has been verified a while ago. Kepler's conjecture this year, using the whole light theorem prover in conjunction with Isabel, because it's more efficient than actually analyzing many cases. But the core of the verification is whole life. Okay, so theorem provers are out there, and they are becoming more and more important, and they are very well represented in our group. We have Jaap, Florian, and Raja working on verification in COC of quantum systems, of quantum computing systems, and the actual swap, because Florian, I would rather list him under Isabel, is Isabel expert, and he frequently gives tutorial and teaches courses in Isabel. All right. So now let me go to describe a particular project that I was involved in, the COCON experiment. And this was the implementation of a conference medical system, think EasyChair or CRP. So all these systems that you use for submitting papers and getting reviews and so on. Okay? So it's typically they are web-based systems. And what we have done, we have formally verified its information flow. Why did we do that? First of all, there are some interesting anonymity and integrity concerns, and they actually pop up quite frequently in systems in current use. Let me give you just an example. This is a message that I received from a mainstream security conference. I received an acceptance notification, very quickly followed by a rejection notification. But, well, I was not home to get this notification, so I only learned about it very late in the evening. Let's say after coming back from celebrating. So essentially this message, this bogus notification message, it's sort of a silly programming error, but still it's a malfunctioning of the system, and this was sent to the authors of 300 papers, who should have been rejected but were bogusly accepted. This means that probably 600 authors on average. So many happy people during a 15-minute period of time.
What system did they, are
They use
their own system?
What's CRP? This is actually used by very many good conferences and exhibits very nice and interesting flows. But actually I was not able to figure out, at the time I was just, so I could have sent them an email to find out what system they used. I don't know. I don't know for sure. But this one is a previous bug in CRP. And this is about some information exposure. You know how in a conference submission system, you have this discussion about the papers, and some comments are supposed to be confidential, like this paper is really bad, but let's accept it because we don't have enough submissions. And then you don't tell this to the author, you just say congratulations and so on. But some of these comments were actually exposed to the authors were able to see them. This was fixed, this was in a previous version of the system. And this is interesting because this is a pure confidentiality violation, so it was really a logical error in the system. This sounds like that. Okay, so there are some interesting issues there, but for me, this was an interesting example of a system that is all about information flow. So it's not about restricting information flow, as in many cases, but about not about forbidding information flow, but about putting some boundaries of the information flow. So it's a study of a system that is, all its functionality is about information flow. And hopefully, gave me knowledge about approaching similar systems of potentially wider interests, such as mail service, web-based mail services, social networks, enterprise systems, and so on. So when I worked on this, I had in mind this reusability and the generality of the verification infrastructure, as I will explain very shortly. So let me talk about the architecture of COCON. We had the Isabelle specification. So basically, the core of the system was programmed in Isabelle, in the Isabelle functional language. We used a code extraction mechanism that I mentioned in order to produce code in Scala. For obvious reasons, besides efficiency, we have this possibility to integrate Scala program with a web environment, with a web development environment. So we had a REST web service wrapped around it, and then a web application at the top communicating with the user. And of course, we did all the verification here, so we have verified it. So the system is what you would expect. It has a notion of users that connect with IDs and passwords, a state of the system. This is a monolithic system, stores papers, authors, reviews, discussions, notifications, and so on. So all this information that is necessary for the reviewing process. The users can take actions such as register papers, upload paper. Committee members can read on papers, assign reviewers, chairs can assign reviewers, and so on. And then the outputs of the system are the PDFs of the papers that you request as a user, you're entitled to, the reading of the reviews, the listing of the committee members, so all these are outputs. So in the end, this is an input-output automaton, abstractly, so to speak, where we call the outputs, we call them, where we call the inputs actions. Okay? This is a big automaton, but just an automaton. And we have designed our verification frameworks to operate on automata with some extra specification that I will discuss in this. So they work, essentially they work for arbitrating input output automata. How did we go about verifying this? We focused, as I mentioned, on or rather we plan to focus on two kinds of properties, but so far we only verified confidentiality properties, such as an author does nothing about his paper's discussion, okay? The kind of preventing the kind of flow that I mentioned. A user does nothing about the paper unless he becomes an author of the paper or a committee in the paper's conference. So you can see here that we have certain conditions under which certain information is declassified. A user learns nothing about the paper but the last submitted version unless he becomes an author of the paper. So if we remove the committee membership possibility, then only the last submitted version will be available, not the previous version that an author can upload. So we see here that we are also talking about a qualitative bound on the amount of information, besides a trigger for the information declassification. Okay? And dually, we have integrity properties. They are sort of, technically they are dual, but they sound quite differently. An author cannot contribute to his paper discussion. This would be quite funny, actually. And this could happen if an author manages to become a reviewer of his own paper. Some of these notions, some of them are serious for this particular application. Some of them really are quite silly and easy to avoid. But keep in mind that what I plan is not only to verify this particular system. So some of these examples are artificial, but they make more sense for other kinds of systems. An author's view of the various versions of his paper is not influenced by the actions of non-authors. This is another requirement, integrity requirement. But as I said, we focused on confidentiality properties, and this is the general pattern of the property that we verified. What, when, and by whom can be learned about the documents in the system, such as papers, reviews, discussions, and preferences. So this is the general question, and we have classified and verified these properties. First of all, stated precisely the bounds in Isabelle, because we have at our disposal the whole mathematical machinery. We don't need to encode this in a particular language. We're just going to express the boundary as precise as possible without the priori restrictions. obviously we pay the price that then the property is not automatically verified when necessary. But we can acquire quite a bit of automation.
So can I, just to give you a break, ask you a question. So you said it is automata, right, in general. So why do you think of something like model checking, or even if you're considering information flow, you can do maybe some type system kind of,
Yes.
Information flow can be checked using type systems and these kind of things.
This is true. And
So
actually,
why this machinery?
yeah, so I care very much about this, and I continuously think of how to model check these things. The problem is that, first of all, the type system is, even type system, most of them, they work for pure non-interference. But some of them, they are extended towards capturing the declassification and so on. But they move from the disability spectrum towards more expressiveness, and they are very far from the kind of property that we want to check here. I prefer to start from expressing precisely the properties and then see how much I can automate with this. And in order to apply model checking, I need to make this either on the fly or as a separate stage. I need to make this finite system. There's an interesting issue about abstraction and refinement with security properties. But I'm not saying it's not doable, it's just that it is an interesting challenge. Basically, sorry?
Which aspect makes this system not finite?
You have an unbounded number of users. Well, first of all, yeah, you have the infiniteness of the data, arbitrary strings, but this is not a true issue. But the true issue is that you have an unbounded number of users and documents.
Is that
Okay, but so you can make, I mean, so basically I suppose that this system is data independent. So at least for the documents, you can just make a kind of
An abstraction.
Right. You can, because it is data independent, so this does not lose anything. But in terms of the users, okay, I don't know.
Yeah, so data, yeah, I agree totally with data. So that is not a real issue, the infinite. I just mentioned it, so it's technically part of the infiniteness of the problem. But yeah, it's the number of users and the number of documents. These are unbounded.
Okay.
Okay, but I mean, we are touching on a very interesting point, because my hope is that I can identify a finite abstraction of the system where you have a certain number of relevant rows. Let's say if you have just two authors and one committee member and one chair, maybe you can have the essence of the system expressed. And maybe if you verify it for this kind of systems, then you are done. Yeah. But you need a suitable relationship with the infinite system.
Yes.
So you need a security preserving relationship abstraction.
Yes.
So this is
I mean,
very interesting.
It seems to me that even more interesting, possibly future work, is that you can actually bound the information. So basically, you don't say that, okay, I mean, there is some information leakage, but you can somehow, well,
You mean enforce it by construction? Or,
No, I mean, so basically, let's assume you have a finite system. Okay, so we have a limited number of users, you have a limited number of documents. Then I want to know, so how do you measure the information leakage?
okay.
In terms of, like, for example, entry.
Okay. Yeah. So you mean a quantitative information?
Yes.
Okay.
You can calculate a number such that you can say that okay, the information leakage is bounded by this number.
Right. So this is so this would be an approach to measure it quantitatively. What I went for was a quantitative description by a formula, which is also in principle integrated in model checker. But for this kind of system, in my opinion, just saying that you have a certain number of bits leaking is not very informative. But if you say that one will not learn anything beyond this and this is sort of a readable statement, a readable specification. This is why I went for this formal description, qualitative description. And this is still quantitative in a sense. So this is still a description of an amount of information, but it is more precise. So it's not trying to quantify the amount artificially. But yeah, so that is something, that is a possibility to go about, and if you tell me how to model check this, that would be actually something very, very nice.
They talk about non-interference.
Yeah, well, it's a form of, yeah, it's an extension of no interference. I'm going to describe in a bit the property that I have.
Maybe we can take it offline, but from my understanding, this was one sort of like order for body checking in a sense, because it's not a safety property.
Yeah, it is really challenging. Yeah.
Trace, one trace, but it's a property of a set of traces.
So, in
And
terms
so in that sense, so it's relating sets of traces which could be possible to relate.
yeah.
And so then...
This is true. So
Yeah,
this is,
true.
there is a
So,
complexity.
in terms of, let's say, if you float on finite state systems, if you want to check, for example, well, let's say,
you could have infinite traces.
yeah, it doesn't matter. But if you want to,
But it doesn't matter when you want to
But-
investigate his question, which is saying like, you cannot learn anything about the system from the outside by observing.
But Florian, so I agree that this is a more difficult problem, but if we manage to actually boil this down to a problem about the finite system, there are some tools, they have developed model checking techniques for finite systems and security properties. But it's way more complicated, it's true, but I mean, as far as my brief understanding of model checking, that it's doable.
you have certain, for example, by summation or summation, like formulas or formulations of non-interference. So you can have, it's not exactly by summation, but
They are called unwinding relations.
Yeah,
in the
unwinding
security
relations.
world, but they are essentially by simulations. Yeah. Actually, let's postpone a little bit the discussion. I'll actually get to the kind of property that I care about. How I model the property. Maybe then we can have a more focused discussion. All right. So these are the properties that we can verify. They are classified according to the source of the information, what I call a declassification trigger, and a declassification bound. So these are listed on the 3 columns. The declassification trigger consists of roles, so various situations that can happen, a certain role that is acquired, such as paper authorship or review authorship, or PC membership, a certain phase, so I put phase steps here in the specification, where the conference has moved on. So this is the time for this kind of system, as well as privileges such as not having conflict with the paper. So these are the kind of situations that can occur, but in principle they can be arbitrary mathematical formulas describing the situation. And then there's the declassification bound, which puts an upper bound on the amount of information that can be. For instance, what can you find out about the reviewer assignment of a paper? Well, you should ideally only find out what is public knowledge anyway, that the reviews are non-conflict PC members and nothing else. So this is a qualitative statement of the boundary. But I'll get to it in a moment. Let me show a little bit the structure of how these are phrased. Essentially, there's a classification of the privileges. Let me take this example as the review document as an example. If you are the author of the review, obviously you can see everything. Okay? Next, in the privilege hierarchy, is the notion of being a PC member in the discussion phase, having no conflict with the paper. Then you can see a bit more. So you can see what's shown in blue here, the last edited version before discussion and all the later versions. Basically, you can participate, essentially this means that you can participate in the discussion of this paper and you can see whatever the reviewers want to make public concerning their opinion. Finally,
you're saying non-conflict PC membership, so what type of conflicts can there?
well, you can declare conflict with the paper, or you can have conflict with the paper if it's your paper.
That this is not allowed.
Well, you can be a PC member and send a paper to the conference. And in this case, the system automatically assigns a conflict.
I mean, there are conferences that you can do that.
Yeah.
Okay.
And you will not see anything about it.
I thought that in most conferences you're not allowed to do that.
I think there are different kinds of conferences.
Okay.
Here you can even be a chair and submit a paper. But then it's a good idea to assign a separate chair. You can assign chairs. You can have any arbitrary number of chairs and PC members.
Okay.
Okay? Next in the hierarchy is normal PC member in the notification phase or paper author in the notification phase. What can they learn? Well, they can learn the last edited version before notification. Okay? They cannot see the previous comments, but they see the last version of the review. Because in the discussion phase, the reviews keep updating, right? But this is not visible to PC members who have conflict and for authors. They do see the final review. Okay? This is how the system operates. So this is a hierarchy of situations, but I really don't care about who can learn things, but about who cannot learn things. So I have to phrase it negatively. I say, for instance, unless one is a review author or is a non-conflict PC member in the discussion phase, one cannot learn anything about the review beyond the last edited version before notification. So there's a negative reading of these statements. Okay? But the intuition is the one that I described before. You have a hierarchy of roles, and each of them may potentially learn more. But I don't care about what they may learn, I care about what they may not learn.
Sorry, I'm a bit lost. This is the requirements you want to achieve, or?
Precisely. This is the specification of the desired properties.
Ah, okay. So you want to basically verify it against these properties.
Precisely. Yeah. How do I know that my classification is exhaustive? Well, if you have a look at the last row here in this compartment, unless a user, or rather a group of users, any member of a group of users acquire one of these roles, and the conference moves into this situation, into this stage, nothing leaves. Okay? So this ensures that my classification is exhaustive. I have essentially covered all the relevant roles. Now, let me very quickly describe a non-standard source of documents, source of information, and this is the assignment of reviewers to a paper. This is a very hot topic. Everybody wants to know who his reviewers are. And the idea would be that, of course, non-conflict PC members who don't have conflict, and well, I will ignore the timestamps for simplicity, they should see everything. So they are excluded from this protection mechanism. But how about paper authors? Well, the idea is really to protect this against the paper authors. And my hope was that they really cannot learn anything. But I wasn't able to prove this. Basically, I was stuck for a few days. The proof one would not go through. And essentially, there's a lot of automation that I set up in there, and it's not easy where the proof breaks or where it breaks. I thought there's something wrong with the design of the system. But actually, there was nothing wrong. It was a tiny bit of information that the authors can learn. They were which differentiates them from the rest of the users. Namely, they can learn the number of the reviewers. So there's a bit of information that is there for them and not for the others, right? So because they know, we assume that, of course, perfect knowledge. So we assume that the system is known how it operates. The secret is protected, assuming that you know everything, even about the system. And since you can only assign one review per paper, they can compute the number of reviews. But this illustrates the fact that I was forced to really state precisely what can be learned. So, and this is a fine control that an interactive theorem prover can offer. So even if I will use a model check here, maybe we can do something together on this, I will still stick to the theorem prover to specify these things. So it's a very nice specification. I will not give up interactive theorem. Okay. Okay, so now the fun part, something that I actually enjoy doing, as opposed to struggling, was having, so once I gathered those results, I tried to come up with a suitable notion to capture all of them, and I had a fight with the literature for a month or so, and I couldn't find the right concept. It was not general enough or versatile enough to cover these examples. And I had to come up with my own concept, and this is essentially, this is an extension of, for people familiar with security, of Sutherland's notion of non-deducibility. It's an extension to handle declassification, bounds, and triggers. I call it bounded deducibility security. And this is a very simple notion. I will try to give its essence. This is the system here. A system execution consists of a list of events. So this is what happens. Now, what can you learn as an observer about some secrets, some values? So so I think some of you may be familiar with knowledge logic or epistemic logic. This is essentially based on epistemic logic. There is a function that gives the secrets from a trace. So the selected aspects of a trace are the values of interest. For instance, the notion of uploading a paper, you don't care about who uploaded the paper, but let's say you care about the content of the paper. So you extract the secret from it. From other events you can ignore, hence the filtering and the mapping component. But you can just think of this V as giving the list of relevant secrets that need to be protected, or the trace of secrets, and then E, a symmetric function that gives the observations. So this is the spy, this is the observer, and these are the secrets. So now we fix some other parameters, the classification trigger, as you saw in the table, and then the classification bound, which is a binary relation on traces of values. And what I want to express, and this fits all my examples, I want to say that unless T occurs, E cannot learn anything about V, or the secrets, beyond B. So this is a boundary for what can be learned. This is an arbitrary binary relation. And this is the definition of the property. Red is the original trace, and we can think of red as the revealer of the secret, of the agent trying to reveal the secret, and of the green as the agent trying to conceal, trying to hide the secret. So, we want to say that for all traces that satisfy the, well, actually this should be the negation of the trigger. Let's say they give some observations and they produce some values. We want to say that there, for what the observer knows, it could have been any other trace that gives values. So any other trace, the alternative trace will be shown in green. But the idea would be that for any values in this declassification bound that I have stated, there exists an alternative trace that produces these values, the green values, and yields identical observations. Okay? So this means that for what the observer knows, this could have been anything within this bound, provided the trigger failed for this trace. Okay? Now, there is some interesting thing going on about an associating by similarity proof, or this proof of unwinding. Since I'm running short of time, I'll go rather quickly through this. The idea is that you have the revealer, that is, as the revealer grows, as the revealer trace grows, the concealer should also grow, should try to synchronize with it. And typically, by similarity proofs are safety-like properties. So the idea is that you stay, the defender or the concealer should stay in the game indefinitely. And if this happens, everything is okay. But in this case, we have some extra constraints here because we actually start with some secret traces that need to be saturated. So we start with a pair of secret traces that are in this relationship, and we have the concealer, as it grows, potentially saturating some of these secrets, or producing some of these secrets. The revealer can react to the moves, can ignore the moves, or can react, or can act independently. But the twist is that at some point, it should not linger behind it is not only about staying in the game, it's also about producing some liveness here. It's also about saturating your own alternative values, provided the revealer has a chance to saturate its own. So this is a combination between safety and liveness approach to staying in the game. Or rather, I should say, staying in the bisimilarity game is not the end of the story. You also have some liveness constraints in here. And this makes the concept a little bit more interesting than standard.
Started late, so you can go on a bit longer, right?
Okay, if it's okay, I'll take until 10 past. Is it okay? I promise not to go beyond. I mean, I know that 1 hour talk is not the most pleasant thing to happen to people. So. All right. And essentially, a bisimilarity consists of a bisimilarity proof, or an unwinding proof, as they call it in the security world, consists of a four-place relation that considers the current states as well as the values of the secrets to be saturated, as well as a strategy for how the concealer follows the revealer.
So this is really bisimilarity. You're not looking at trace equivalence.
Well, it is. I mean, yeah. In the end, I established a form of trace equivalence. Well, it's not trace. It's a security problem. So it's a property. As Florian mentioned, it's a property on set of traces.
On set.
So essentially, a system. If you think of a system as a set of traces, the system should satisfy the property. It's not that if I verify the property for each trace of the system, then it holds for the system. You see, it involves a revealer and a concealer. So it's for all existing property. So this is the format of security properties, but there is a certain twist in this. All right. In summary, so we have this generic parameterized notion of security, an associated unwinding proof method, and we have instantiated it to that exhaustive classification of the relevant things that can happen in the system. And I'll be very happy if we can continue the discussion that we started about model checking this. I thought a lot about this, but couldn't find a proper way to do this. All right, and we have published this in CALB in 2014. There I have a much longer discussion about what happened there, about the decisions that we had to make, and about how we handle the complexity of the beast, modularizing and so on. I did not discuss this. Okay. So, a summary of the formalization. We spent 1,000 lines of code on the BD security framework, including the soundness of the unwinding proof method. This was the bulk of the verification, actual confidentiality properties, even though we divide the strategy language and we were very careful about stating this as compactly as possible. It still took 10,000 lines of code. Even more reason to try a more automatic method. And then we have some safety properties that we use as auxiliaries or complementaries for the confidentiality properties, and something that we call forensics. Let me give an example of how safety combines with confidentiality to ensure the actual desired effect. Actually, the example already popped up in my previous discussion. We prove things like confidentiality property says only non-conflict PC members may learn such and such, for instance. Okay? But then the authors are always in conflict with their own papers. The system ensures that this is a safety property. You see that the safety properties took very little. I would say that they are almost model checked. So the Isabelle automation here is very good, and we just have to specify them, do an induction, see where it failed. We have sort of a failure trace, similar to what model check would give, and then tune it until it works. So we discovered lots of bugs of the system by verifying loads of safety properties, but the verification was almost automatic. So let's say we verify that authors are always in conflict with their papers. This is particularly true for authors of bad papers. And then we put these two things together to obtain that authors never learned such and such. Okay? So in order to verify what we want, we need sometimes to customize the general purpose properties that we listed there in a certain format. Now, concerning forensics, this is a very nice name, I'm very proud of it. It has nothing to do with the area of security that is called forensics, but it has something conceptually, but it's not sort of mainstream forensics. What is this precisely? Well, after we proved that one cannot learn beyond such and such unless one is or becomes such and such, this is the format of the properties, we thought that we are done, but actually there was the question, but how can one become such and such? So we showed that only an author or only a committee member can learn this. But then can a malicious user become a committee member on covert channels and have to take care of this extra bit as well in order to relax? And we did a little bit of backwards reachability in the system, essentially showing that, let's say, how could a user become an author of a document? Well, the only possibility is that the user registered the document or he was appointed by somebody who registered the document and so on. So there's a backwards reachability situation that should not be influenced about what happens in the rest of the system. So essentially, it's a form of separation. Again, a form of data integrity, integrity, a security problem, essentially. But that went on very easily using Isabelle's induction mechanisms. So only after we verified confidentiality, safety, and forensics, we were fine with our final specification and verification. All right. Now, what we want to do next is actually take care of the extra layers, because we pretended that the system is an input-output automata, and this can be true about the Scala program. This may actually be true for the same REST web service. This may be a valid abstraction, but there could be many things happening in the web application, and we want to use very automatic, more automatic tools to verify this part and combine it with the verification of the kernel. All right. Now, here's the funny part. We have actually used the system, and we have used it for a real workshop, well, our workshop, and we are going to use it for the Tableau conference. Hopefully, we managed to. Hans Denivel is the chair, and he's quite enthusiastic about using it.
So this is going beyond the POPL trend where now we have to verify all the papers that are published in POPL, now we have to verify all conferences.
Yeah, that's a bit like, well, you have to verify the authors. Yes.
So the verification is carried out on the level of system or on the level of code? So like
The
verify the...
Yeah, we verified the Isabel code. Okay, so we wrote a functional program in Isabel. That's what we verified. But this is not what we have integrated with the rest of the system.
Okay, so you basically use this code to model the let's say, your understanding of how for example, the chair works.
Yeah, but it's not just a model, it's an executable specification. So it's actually something that you can run. It's an input-output system. And it's a faithful specification of the whole system.
I'm just curious, because you have like basically two types of verification. You deal with models and LTS structure or whatever. And also you can verify the source code. Like, okay, you have like, because those EVGL systems, they must be like written by C code, Java code,
Right,
whatever.
So here we aim for security by construction.
Okay, so
I mean, this is what we built our, initially I actually wanted to verify EasyChair, but I realized that it's not such a, I mean, it was not built having security in mind. Here I have, so you can call this a model, and I have lots of discussion, with model checking people, and they typically like to call this a model. I like to call this an implementation. This is an implementation of the system. The model is isomorphic with its implementation.
yeah, okay.
But again, so if you trust the code generator. But even if you trust the code generator, this is not the end of the story, because you have the web application around it. It's a different thing. But we have verified a big model, that is a faithful representation of the system, not an abstraction of the system.
So, I mean, I have a comment here. So, one of the things, I mean, somehow this also gives me the flavors of process algebra when you're talking about bisimulation. And maybe I was even thinking of FDR. Are you familiar with FDR? Yeah. And so, one thing we've been considering is sort of maybe modeling quantum systems using process algebra and then actually proving theorems about that, right? And maybe that's one way of doing instead of, encode sort of these things into a process algebra and then prove properties about that, the processes involved rather than, so maybe that's one.
I was actually also very fond of, I don't know what FDR stands for, it's rings a bell.
Failure, divergence, and
refinement.
refinement.
Okay.
FDR is just it's a system.
Oh, it's for system.
So you have in my opinion, much better similar tools, let's say.
Okay, I mean, no, some of these, he's talking about bisimulation, but I think he's really talking about some trace properties, maybe like refusal sets or...
Well,
Yes, FDR is basically based on this fairness dimension.
Yeah.
So I don't think it's a fight. So I don't think it's that kind of semantics for CSP. I don't think it's targeting security properties.
No,
it's
they have. I mean, it's basically you have to encode the security properties in terms of trace properties. Then this,
okay. So this is more like control. So it's like an access control property that approximates a security property.
Yeah. security, approaches discussed here, I would say, so, this is more or less how to say, non-interference things.
Well, in a way, it factors in the classification. That's the main difference. So it has a similar nature with non-interference, but it puts the classification bounds. You have to say it don't interact. It says interact up to a certain level.
Yes.
Yeah. But even beyond this, the particular choice of the trace model and so on, using process algebra is an interesting prospect, and I had to fight with my co-author about. So I was really for a distributed environment where I would model this as agents in a process algebra, but then he convinced me to go for a monolithic system. But that's a valid alternative, and in the end we would face the same problem with reducing the state space to a finite space. So maybe we have the right environments to talk about the problem better.
Yeah, so just to add to this, I mean, there is Casper, right, for example. So there's some security thing based on FDR.
So an extension for...
Yeah, maybe I'll have a look at it.
Yeah, there are lots of very cool things there, including the Jeeves tool that allows you to actually program complex systems, and there's a sort of a monitoring system that is running like an extra thread that makes sure that you cannot do anything wrong. So basically, if you happen to do something wrong, you don't notice it because the monitoring tool breaks it. So that's again a paradigm of security by construction.
Yeah, but that's for the running phase. It's not design phase.
Yeah, but you know for sure that your specifications are okay because they are monitored. Yes. So I mean, the downside is that you can design it wrong and not know it.
Yeah,
you are not going to understand your own code in some results. But it's compared to interactive verification, even monitoring sounds less daunting. So I would like to explore alternative ways to go about this or to improve automation. Because in the end, it's not that bad. So in the end, after you specify the property, you set up the right automation, it has some similarity with model checking. So it's not like we were like 1,000 people working like slaves on this. It's not that bad, but still we'd like to combine the different approaches. All right. Okay, so now concerning the usage of the system. First of all, what I'm going to tell you needs a little bit of preparation so that you don't use it against me. Bug finding is, in my opinion, metaphysics. It's an absolute matter, but verification is dialectics. It is a never-ending process. It's always based on a model of reality. And as soon as you have verified that your computer works up to the operating system level, up to the hardware and so on, there can still be, I don't know, a star emitting a certain kind of radiation and modifying the state of your computer. But this is not the kind of thing that I want to talk about. I want to talk about the limits of our model, more mundane limits. First of all, there were some bugs about the system. We haven't verified the functionality of the system. We only verified that it doesn't leak. So there were bugs like any other system, just like any other implementation. And there was some despicable behavior by some of my colleagues who helped me test this, such as rebellion. So the first version had an author who was able to get all his papers accepted by declaring conflict with everybody. So there was a default value in there. This didn't violate any security property. Even worse, there was voyeurism. In one corner case, a reviewer was able to read the other reviews before uploading his own review. And actually the system knew about this, but did not show it. This is a very interesting property. This is the opposite, not the dual, but the opposite of confidentiality. It is about revealing things. So of course, a reviewer can read the other people's reviews in the discussion phase, but typically only after he uploads his own reviews. So basically one should see that he has uploaded his review. Otherwise, you will think differently about his later decisions. So basically, one is like a contract. You want to see what he writes when he sees what you write as two reviewers. But actually, if the list was empty, the system was not showing that the list was empty. So it was a concealment of information, undesirable, which looks like a confidentiality violation. But again, it didn't violate the properties that we verified. Now, during these our workshops,